Hello, it's Keith here, and this is lesson 2 of the so-called Mintile series of my 68,000 assembly programming tutorials. Now, we're looking at this so-called Mintile program today. That's my minimal tilemap example, which is multi-platform. It exists on Z80, 6502 and the 68,000, and we're looking at the X68000 version here just as a random selection. It works on all of the systems in my tutorials, but it allows us to have a tilemap, and it allows us to simulate sprites. They're not real hardware sprites or anything. They are software drawn using the same code as the tilemap. And the reason we're doing that, using the same code for both, is it means we can port to more systems more quickly, less code to port. Now, we can move an object around the screen, and we can also scroll the screen. If I hold the fire button, we scroll a total of 3 extra tiles. There's sort of 4 off-screen tiles, and so we can use that as a scrollable area. So what we're going to look at today is some of the sprite code. Now, specifically what we're going to look at is the code that actually does the initial drawing of the sprite, but then also the code that actually handles the cropping, which is based on the code from my original series, the sprite clipping simple examples that I did. So it's pretty similar to that, but it's been changed a little bit. So you might need to see that if you've seen the other series. Anyway, let's go over to our code and let's take a look. Okay. So the first part we're going to look at is the draw sprite. Now, the first thing to discuss is how we're actually sort of dealing with the sprites. The sprites have a variety of parameters that we're going to load in. Now, these are all referenced by offsets to an object, a sprite object, which is passed in A4. So we're going to load in various parameters from that sprite object, which we're going to assume is pointed to by A4 here. So the first thing we're going to do when we want to draw a sprite is check if we actually need to draw it at all. So we're going to check the sprite refresh flag, and if that is 0, then we're simply going to return because the sprite maybe hasn't moved, there's no reason to redraw it, so it won't. So in that case we would just return. We've got a function here to flag the sprite for refresh if it's moved, if it's been overlapped as well, we would want to do that. And then when it actually comes to drawing the sprite, we're going to actually have to sort of start loading in the various parameters of the sprite itself, again all from the A4 pointer. So the first thing is the actual tilemap of the sprite. Now, as I say, we don't actually have any literal sprites. What we have is a background tilemap. That is our background tilemap, so that's our background, and you can see the invisible off-screen areas marked there. And then we have small tilemaps for our Chibico mascot, our character, and so that is actually a miniature tilemap that's being drawn in an irregular position on the screen. The main tilemap's always in the top corner. The Chibico can be wherever we want it to be. So as I say, we're calling it a sprite, but it's actually a miniature tilemap. And so what we're doing here is we're loading in the address of the source tilemap into A2 here. What we're then doing is we're loading the X and Y position of the sprite. We're backing those up for later because when our sprite moves, we will need to redraw the background in the old position. And we're then loading in the pattern data. Now this will vary depending on the system, but on the majority of the systems we're using bitmap data, and so we have somewhere some kind of bitmap data for our tiles for our Chibico character here. It's actually the Sam Coupe version, same as the Sam Coupe version for this system. So we're loading in the pattern data or an offset to the tile, depending on the system, if it's a hardware tilemap system. So we're loading that in here. Now, what we're doing next, and we've got some custom code for the Amiga and the Neo Geo. Now, these systems can't really flip the graphics in software. The Neo Geo is working from ROM tiles, so we can't flip those in real time. We can't calculate it. It's in ROM. So on the Neo Geo, we're actually using a different set of patterns. And on the Amiga, we're using the blitting in a lot of cases, and so again that's a memory copy routine, so the memory, we've got some defined flipped patterns somewhere else that we're going to use for that. So a couple of custom tweaks for some systems that are a little bit stubborn, shall we say. So what we're going to do next is we're going to load in the width and the height of the object that we're drawing. Now, the XY position, width and the height are in the same kind of logical units as the clipping examples I did in the past. This is something I'm kind of adopting as a standard now, which is one logical unit is 2 pixels. This worked very well for 8-bit games because the vast majority of the systems I'm working on are either 256 pixels wide or 320 pixels wide, and by using one logical unit is 2 pixels, this allows for a 256 pixel wide screen to have an invisible border for cropping, or a 320 pixel wide to simply fit within a 1 byte x coordinate. So I'm sort of keeping that as a standard now. By standardizing on that, it doesn't particularly reduce the capabilities of the better systems like the 68000, and it allows on the 8-bit systems to transfer the programs between multiple systems. I can reuse bits of my code very easily. I suppose as well on the 68000 or 32-bit systems, then maybe I could add an extra byte to add an extra bit to the 8-bit value if I needed single pixel precision. That would probably be a convenient way of doing things. Anyway, so we're going to run our do crop routine, which is a modified version of the one in the simple series. Now, the modifications are to work in tiles, but it's also able to flip. It can flip. We can do X flipping of our sprite, and we need some code to handle that. So that's one of the things we've got there. And so before we do the crop, we're loading in the flags. The flags, in the case of this example, the only flag that we've defined is the X flip flag. So that's all we've got there. So we're running our crop, and if the carry is set, then the entire object is off screen. So we're just simply going to give up. If the entire object isn't off screen, then we're going to draw it to the screen. Now, we're always working in tiles, so we can't draw half a tile. The code, we're reusing our tilemap code. It can only draw full tiles. So we're converting the width and height in logical units to a number of tiles. We're effectively dividing the logical units by 4, and that is calculating the width and the height in blocks of 8 pixels. And you'll notice if we're partially off the screen at the very edge, if we go below a single tile's worth of value, parts of our object will disappear, just because, as I say, it's very limited, this version of the sprite code. You would want to create more advanced versions that could do partial tiles and things, but that would make the platform specific code much larger, take a lot of time. I don't have time for that, so I'm not going to do it in this case. It's a simple example only. Now, we're then using the platform specific get screen pos routine to calculate a VRAM destination. That's going to be different for every system, completely different, so there's nothing constant there. Now, we've calculated the width and the height of the drawn tile map here with these commands here, but after each line of our graphic, we're going to need to start drawing the next line. And so if we've only drawn half of the tile map to the screen, we're still going to need to be able to recalculate the start of the next line. So we're loading in the full width of the tile map uncropped here into D7. And again, we're converting that to a number of tiles. Now, the final thing to do is we're either going to draw the tile map or we're going to draw the tile map reversed. And we've got the check of the flags here, and we're going to jump to the according routine here. Now, we looked at those tilemap routines last time. These are just simply a routine that repeatedly runs the do strip command, moving down a line after each time, and the reverse version simply uses the alternate drawing routine. Now, those drawing routines, platform specific codes, so we're going to cover those in later tutorials. We're not going to cover them here. So the final thing we're going to do is we're going to discuss the cropping. So if we imagine that this is our sprite, and our sprite might be partially off the screen, we're going to need to remove parts of it. Now, when we remove parts of it, we're going to need to change the X position and Y position potentially, because that would be a Y position that's off the screen, so we'd need to change that to 0. We'll need to skip tiles that are off the screen, and we'll need to change the height and the width accordingly. And so that's what we're going to do. The other thing we're going to do, though, is we've got a flipping routine, so we can X flip our sprite like that. The problem is that parts of the code are rather crude in the way that they deal with that, and so we're going to have to make some compensations, because, as I say, parts of the code, I've kind of tricked the code into doing it. Parts of it really aren't very good at it, so you'll see some mathematical corrections around the place to get it to work. I am working on a more advanced tile mapping routine called max tile, which is far more complicated, unfortunately, far more platform specific code. It can do X flip, it can do Y flip, and it doesn't have as many glitches. So we'll see that in a later lesson, hopefully. Anyway, so when we run do crop, the first thing we're going to do is we're going to bit test bit 0 of our flags. If that is a 0, then we are not flipped, and in that case we can just start cropping away. Otherwise, though, we're going to actually need to, basically, we're going to need to flip our coordinates. So if our sprite is over here, we're going to pretend it's all the way over here and do the cropping for that, and then we're going to flip it back again. The reason for this is if our sprite is flipped the other way, the width calculations are going to be wrong. We work right to left on our source tile maps when we're drawing from right to when we're X flipped, and so by moving it to the opposite side of the screen, those calculations work correctly. This was easier than doing a second do crop routine, basically. So that's why I've done it. So what we're doing here is we're adding the width of our sprite to the sprite's X position, and then we're negating it, effectively flipping to the other side of the screen. We're then doing our crop, and if that crop doesn't result in a carry, meaning if it's entirely off the screen, we're then going to flip it back again. So what we're doing here is we're taking the screen width with a correction to adjust, because otherwise it was creating some errors. As I say, there are some unfortunate mathematical imperfections in this version. The new version is going to work in a better way. And then what we're doing here is we are subtracting the width of the screen and the width of the sprite from the new X position, and this is resetting the X position to the other side of the screen, and this is all so that we can calculate the correct crop of the source data if the sprite is flipped, because as I say, we're going to be working with the data in the reverse position. We don't flip the tile map, we read the tile map in the reverse position, in the reverse direction, and so we're having to do these mathematical calculations to get it right. That's how this version of the tile map code works. The max tile version I'm going to use to replace this, I'm actually pre-calculating the tile map into memory, and I'm flipping the tile map so that this isn't necessary. It's kind of, you know, you make these choices and they all have advantages and disadvantages, and unfortunately the mathematical problems that this one caused for me were regrettable, but as I say, it is what it is now. So basically we're now going to look at the cropping routine. As I say, this is based on the version that I used in the original Simple series, but it's been modified a little bit to work in tiles. So what we're going to do is we're going to use D2 and D5 as our temporary variables. So these are going to calculate our cropping, and we're going to look at the Y position first and then the X position second. So the first thing we're going to do here is we're basically going to take the Y position and we're going to subtract the minimum visible Y coordinate, because the coordinate 0 is actually off the screen, and so this is effectively moving the Y position and subtracting that minimum Y, that position here, and this will move that Y coordinate. And if our object is off the screen in that kind of way, then this will cause a carry. Now if there's no carry, then we are entirely in the middle of the screen somewhere or further down, so in that case we don't need to do anything. But if it's not, then we do need to do some kind of cropping. So we're negating the resulting Y position because we've gone negative, and we're then rounding this up because we want to calculate this as a number of tiles. Now we can't draw a partial tile, so if our object is partially off the screen, we're going to need to round that up to a number of tiles and offset the first draw position to the correct position for the number of tiles that have been removed. So what we're doing here is we're seeing if the number of tiles we're going to remove is the entire height of the sprite, because if it is, we're entirely off the screen and we would want to give up. However, otherwise what we're going to do is we're basically going to calculate the number of tiles we need to remove from the top. We're doing that here, and then what we're doing here is we're calculating the new Y offset for the remaining tiles that we are going to draw, because if we've removed one full strip of tiles here, that would cause our sprite to jerk up in 8 pixel blocks, but we want to at least move it smoothly as we're removing those 8 pixel strips, and so we're calculating the offset for the remaining pixels here. And so that means that even though 8 pixels are removed, we can still see a smooth movement as our sprite leaves the top of the screen. Okay, so and what we're doing here finally is we are storing the new Y position, which has now had the minimum Y logical position subtracted from it, and so we're one step closer to the true Y position for the screen. Okay, so we've done the top crop there. Now what we're going to do is the bottom crop. So we're adding the height of our sprite in logical units here, and we're then going to subtract the entire height of the logical screen. Now if this causes a carry, then our sprite must be somewhere on the screen, and in that case we don't need to crop. If it's not caused a carry, then that means that actually our sprite is at least partially off the bottom of the screen. And so what we're doing here is we're converting this to a number of tiles, and then we're seeing if that's the entire height of the sprite, because if it is, our sprite's entirely off the top of the screen, and in that case we're going to give up. Otherwise, we're storing that in D2, that's the amount removed from the bottom. D5 is the amount removed from the top, and we now have our crop for the top and the bottom of our sprite. So what we're doing here is we're adding those two together, converting it to a number of tiles, a number of 8 pixel blocks, and if that is resulting in a 0, then there is nothing to crop. But otherwise, we're negating it and we're adding that to the height, effectively updating the height, removing any parts that are off the top and the bottom. Now, this version of the code actually can't crop an object that is bigger than the entire screen. There is a sort of a bug in it, if you will, that it can't cope with that combination. But I do have, with the MinTile version, I am compensating for that, so you can define objects that are bigger than the entire visible screen if for some crazy reason you wish to do that. But anyway, so that's calculated our new height here. What we're then going to do is we're going to remove the tiles from our source tilemap address if our object is off the top of the screen, because we're going to need to skip the first few tiles that are defined within our tile data. So if our Chibico is half off the screen, we're going to need to skip half of these tile numbers, and that's what we're going to do here. So what we're doing here is we're basically converting the width of the object to a number of tiles here per line, and then we're calculating the number of lines that we need to skip here. We're multiplying the 2 up and we're adding that to A2, which is our source tilemap address. So that has skipped any tiles that are basically being missed because the object is off the top of the screen. Okay, so we've cropped the top and the bottom. We're now going to crop the left and the right. So we're clearing our temporary variables, we're going to reuse them, and we're basically going to do the exact same thing again, just looking at the X position and the width this time. So we're basically going to move our X position into D0, subtract the minimum visible X position, that's the far left of the screen over here, and then again, if that has caused a negative value, then our object must be partially off the screen. So if it is, we're converting it back to a positive, rounding up to a number of tiles, and seeing if that's the entire width of our sprite. Maybe our sprite's entirely off the screen. If it's not, that's the amount we need to remove from the left. We are then basically calculating again the offset for the object parts we are going to draw on the screen so that we get that nice smooth movement on the left hand side of the screen here. And we're then updating the X position here. Okay, we've done the left. Let's do the right. So again, we're adding the width of our sprite, and then we're subtracting the entire width of the logical screen. We're sort of basically going to look and see if our sprite is somewhere like this. And so what we're doing here is if that has caused a carry, then the object must be entirely on the screen, but otherwise the object must be partially off the screen. And so in that case, we're seeing if it's the entire width of the sprite that's off the screen. If it is, then we're entirely off the screen. Otherwise, that's the amount to remove from the right. Okay. Well, we've calculated our crops again. So we're adding the two together here. We're converting it to a number of tiles, and again, seeing if there are any tiles we need to remove. If there are tiles we need to remove, we are basically subtracting that from the width here. The width is still in logical units at this point. We do convert it to tiles later, but I like to keep these cropping routines in logical units for consistency. And then once again, if our object, if you think of like the star as being the first tile here, if our object's partially off the screen, we need to skip some of those tiles. And so that's what we're doing here. We're converting the amount removed from the left to a number of tiles and adding it to A2, which is our source tilemap address. Now, at this point, we're finished. So all we do is we clear the carry. That's what we're doing there. Now, in that case, we return and we get on drawing our sprite. But if at any point we've found that there's nothing on screen, we're jumping here, which sets the carry and returns. And that tells the calling routine, hey, I've got nothing left to draw. Please give up. You're wasting your time. So there we go. So that's all we're going to be covering this time. Now, what we're going to be looking at next time is some more of the tricks that I'm using with regards to the sprite drawing routines. This routine on the 68000 systems even only uses a single buffer. It's not double buffered. That's not very logical on 68000 based systems because they've all got lots of memory. But for consistency, I wanted this to work in the same way as all systems. And actually on the Sinclair QL, double buffering is a problem because of the way the memory map works. So as I say, I wanted to give myself a challenge. Mintile was supposed to be a minimal tilemap to see what I could do, the most I could do with the least available, and so it doesn't use a double buffer, and that means flickering. And so I've come up with some ideas to try and reduce that. We'll see those next time. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.